All right. It's great to be here, and to see your talks. It actually brings back memories of me in the late 80s, in particular in 1987 when I was an undergraduate math major, but wasn't sure if I wanted to continue in math. And by just a strange stroke of luck, ended up going to one of the very first REU programs that existed. And it ended up really profoundly shaping my future and kind of being one of the events in my life that led to me going to graduate school in math. So I enjoy watching you guys maybe following similar paths. All right. Okay, so as Vitaly so eloquently put it, this talk is about ergodic theory. And ergodic theory in the context of some very special dynamical systems. So I'm going to start my talk with a very simple, you almost might say it's a mathematical parlor trick. And so some of you might have seen this before, but I really want to get to the underlying dynamical rationale for why this phenomenon takes place. And then I'll start saying just a tiny bit about dynamical systems and another type of dynamical system with very different features. And then in the end, I will pose for you a question that is open and fundamental in my current field of research. Okay, so let's start with the parlor trick. So our parlor trick is it's a mathematical one, so any connection to real world problems is ridiculous, basically. So let's suppose that we have an investment, and we start with $1, and this investment every year returns 100%. So in the second year, you have $2. Okay, this is all just by way of introducing to you a sequence of numbers that we are all familiar with, that is the powers of 2. So in the first year you have $1, the second year you have $2, the next year you have $4, and so on. Okay, let's look at this list of numbers growing at some astounding rate. And let's say that you just keep track of the first digits of these numbers. Okay, so 1, 2, 4, 8, and so on. And let's look at that list of first digits. And here's the question I pose to you. What percentage of numbers on that list are ones? Okay. Does that even make sense? So how would you compute a percentage of a digit in an infinite list of numbers? Well, there's a well-defined way to do that. You count, you go out to the first n numbers, you count the number of occurrences of 1, you divide that by n, and if the limit as n goes to infinity of that fraction exists, then that limit is the percentage of ones, okay? So what is the percentage of ones? Does that even make sense? Does that limit exist? And of course you can ask the same question for 2s, 3s, 4s, and so on. Now, if I gave my talk just about this subject, I could go on and on. It's a fun subject. You can also look at other lists of integers and ask what are the percentages of various first digits. And there's something called Benford's law, and blah, blah, blah. Okay, but we're just going to stay very focused in this talk. So I conveniently have computed for you the fractions of powers of 2, beginning with 1. So for the first 10 powers of 1, 4 out of 10. So, and I did the same thing for 2. So here we have 4 out of 10, here you have 2 out of 10. First 100, you have 31 here and 16 here, and so on up to, so this is the first, what is that number? Is that 1,000,000? Yeah, that's the first 1,000,000 powers of 2. I can compute the first digits even though I can't write down the numbers. Okay, so here we have what appears to be some convergence going on, right? So this seems to be converging to a number close to a third. It's pretty big, and almost double the number of numbers whose first digit on this list begins with 2. So what's going on? So, well, let's do it for all numbers, all digits. So here we have a histogram of the first digits, so 1s, 2s, and so on up to 9. And you see that, indeed, for the first 100 years, this is the most common digit. And there's a bit of fluctuation, but there seems to be a downward trend as the digits get bigger. Here's after 1,000 years. It looks much more regular. And now we have a definite downward trend, 100,000 years and 1,000,000 years. And it seems to be very clearly converging. So if you had to guess, you would guess that there is an actual limiting distribution of first digits in the powers of 2. Yeah? Okay. And what else was I going to say? If you think about it, you can sort of figure out a heuristic for why this should be true, right? So if I have a number that begins with 9, a first digit, you can easily determine that when I multiply that number by 2, the first digit has to begin with 1. So you can't stick around in 9 for very long. But if I have a number that begins with 1, it's actually possible to begin with 1 after you multiply by 2 if there's an appropriate carry. So, where's that? Yeah, that's right. Or maybe not. But anyway, there's some heuristic that I can't remember. But you think of your own heuristic. But it's a heuristic, right? We're mathematicians. We're interested in seeing if we can actually prove something, really prove that is the correct picture. And so I've drawn a curve that fits these data very well. And I'm going to say more about that curve in a little bit. OK. So how do we analyze this problem mathematically? You have this list of numbers that's kind of unbounded, and you're trying to, I mean, the numbers themselves are arbitrarily large, and you're trying to say something about the statistics of this arbitrarily large collection of numbers. And statistics are things that don't work really well on the integers, talking about statistics of the integers. That's a tricky thing to do. So what I want to do is translate this question into a compact question, sort of a much more manageable question. And the reason I can do that is that I'm looking at some very finitary information about this list of huge numbers. I'm just looking at the first digit. OK, so let's write down mathematically what it means for the first digit of a number to be 2 or 3 or whatever. OK, so we learn in our high school chemistry or physics class, I guess, to write numbers in what we call scientific notation. So any number can be written as a number between 1 and 10 times a power of 10, right? So, and this is called the mantissa of the number t, and this is called the exponent. So here, this is a real, this is a positive real number. This is, oh, well, this is any number. But if t is positive, then this, this is a positive real number, so that this is positive. And this is, this could be any integer. So this could be less than 1 or greater than 1, depending on, or sorry, less than 0 or greater than 0, depending on whether t is less than 1 and or greater than 1. OK, so let's suppose our number is written in this unique form. OK, this is a unique way to express all numbers. And what we're interested in is the first digit. OK? And I claim, and this should be pretty obvious to see, that the mantissa carries all the information you need about the first digit of the number, right? So maybe this is going to be a little bit labored, but let's go through this. So for example, this number in scientific notation is 1.2 blah, 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 times 10 to the 6th, right? And this mantissa here is what tells us what the first digit is, right? So the integer part of the mantissa in this case is 1, and the first digit of this number is 1. OK. So this should be a believable claim. The first digit of t is k, exactly when the mantissa lies between k and k plus 1. Okay, so it has to be less than k plus 1 and greater than or equal to k. Okay, so for example, first digit is 1 because the mantissa lies between 1 and 2. Okay. Now I'm going to do the crucial thing. I'm going to take the log base 10 on both sides. So I think if you gave this problem to anyone back in the 1950s, and they were dealing with large numbers, and they wanted to be able to say something about very large numbers, the natural thing that they would do would be to look up that number on a log table. So this step of taking a log base 10 would be a very natural step to someone back in the 50s, because that's how people back in the 50s dealt with large numbers. You had to multiply large numbers, you took their logs, and you add them. Now, nowadays, this thing that I just did might seem a little weirder. I think people are a little less log-friendly than they once were. Okay, so but if I take the log of both sides, by the property of logs, we get this. And if we simplify this, the log of t is the log of mantissa plus the exponent, which is just an integer, remember? Okay. And so what we've done is we've gotten a different characterization using logarithms of what the first digit of a number t is. So just rephrasing what I said before, the first digit of t is k, exactly when the mantissa lies. Okay, so I said that before. I did actually write this. Some of these slides were written for a general non-mathematical audience, which I think just totally blew them away. So I'm hoping that it doesn't blow you away, but maybe it seems a little elementary. Okay, so but the first digit of t is k, exactly when the mantissa is in that interval. And so the first digit of t is k, exactly when the log of mantissa lies inside of the log of that interval. All right. And how do we obtain the mantissa from the log of t? Log of t is an easy thing to compute. Log of mantissa is maybe a little more mysterious. Well, here's the beauty of it. This is an integer, and this is a number. Since the mantissa is less than 10, this is a number less than 1. So if I break log into these two parts, this is the integer part of the log of t, and this is what's left, the so-called fractional part. And so rephrasing this statement down here, the first digit of t is k, exactly when the fractional part of the log of t lies in this interval log of k plus 1. Now, fractional part of log of t we can draw a picture of. So there's log of t, right? So that's defined on the real line. And now let's start cutting this graph at integer values. And to take the fractional part of log of t, we just subtract off the integer value that it crossed most recently. And so these pieces slide down. And now we have a picture of the fractional part of the log of t. And it's a function with kind of infinitely many branches that get flatter and flatter. So this is the function down here that we use to determine the first digit of a number. So pictorially, I've just scaled everything up so you could see it better. So here's my number t. I take the fractional part of the log of t, so there it is on the graph. And I go over here, so there it is, it's the y coordinate of that. And now to determine what the first digit of t is, I see which interval it lies in. So in this case, it lies in the interval log 3, log 4, which makes sense because t here is between 300 and 400. So that's just a check. Okay. So there's my function f. Okay, so now let's do this problem for the first 9 powers of 2. Let's look at what those first digits are. Okay, and then we'll start to see a pattern. So, so here's, okay, here we go. Boop, boop, boop. Yeah, there it goes, okay? So you see we're reading off kind of the fractional part of log t for these first 9 powers. And here we see, here we start to see why the first digit of 1 should be more common than these other first digits. Because while these numbers seem to be spaced in a very uneven, or not, in a very stretched out way on the real line, if we take the fractional part of the logs of these numbers, they seem to be even, more or less evenly spaced along in this interval 0, 1. And if that's actually true, which it is, then, well, clearly the amount of time we spend in this interval is going to be much bigger than the amount of time we spend in this interval, right, and so on. So this explains the relative scarcity of the first digit 9, or at least this picture heuristically does. All right, well, it's not a large mathematical step to go from this, to see why this heuristic might be true. It's not a large step to see why this heuristic might be true. So it's not a large step from this heuristic to another heuristic, basically. But let's do it, okay? So let's view this again on the log scale. So I'm just going to draw exactly the same picture I drew before. So here are these first digits, and here are these numbers pretty nicely spread out. Okay. Now I want to do this a little bit in more slow motion. Okay, so here's 2, and there's the fractional part of log 2, which is, well, since 2 is less than 10, it's just log 2, right? Okay, here's the fractional part of log 4, which is also less than 10, right? So it's just the log of 4. But now notice, by the properties of log, since this is 2 squared, this is twice log 2. So to get from here to here, excuse me, I added log 2, log base 10 of 2. Now let's go to 8. Okay, here I add log 2 again, right? 3 log 2. And since 8 is less than 10, it's just the log of 8. What happens when we get to 16? Oh, okay. This illustrates what I was saying. So these are evenly spaced intervals here of length log 2. Yeah? So what happens when I get to 16, the next number in this sequence? Okay, sorry. This number alpha, by the way, is approximately 0.3. Okay, so what happens when I get to 16? Well, I fall off the face of the earth. I'm no longer between 0 and 1. But nonetheless, if I want to figure out where I am, where the fractional part of log 16 is, first I take the log of 16, which is 4 alpha, and then I take the fractional part of that. And that means subtracting 1. So that means I take this number, and I had to put it over there. So you see what I just did? I hopped over here by alpha, and then I cut off the part there. I took all the what's left when I subtract 1, and I just moved it over there. And then I could continue again after that and add alpha again, keep going. Okay, so here's 5 alpha, which is the same. So here's log 32. And taking the fractional part of log 32 is the same as taking the fractional part of log 16 and then adding alpha. So what I'm trying to say is this sort of operation of going on and on and on to keep track of what the fractional part of the logs of these numbers are, you are perfectly permitted to make the problem simpler by first taking a fractional part and then adding this alpha. So that's why it's easy for me to produce a table of the first digits of the power of 2. I don't have to, I write a computer program, I don't have the computer program compute the first digits of powers of 2. That would be insane. What I do is I take log of 2, and I multiply it by n, and I just take the fractional part. Or I could even do it better than that. I could just have a program that just adds log alpha, right? And then when it gets bigger than 1, it goes back into the interval, and I just keep adding log alpha. Okay. And so on. Okay, so now this is explaining how this number of digits is produced. And you can see this sort of equidistribution that's going on. So, well, we're taking everything mod 1. We're taking the fractional part, right? So I claim that what we were doing on the previous slide is the same as taking this unit interval and gluing together its two endpoints. And what the previous slide was saying is that I can take this unit interval, mod 1, and the points that I get by doing this translation by alpha in this interval mod 1 are precisely the fractional parts of log alpha. So I might as well glue these two endpoints together to get a circle. So we're just going to draw a picture of what we're doing here by adding this alpha repeatedly. So there, yeah, there it goes. So you see, whoop, right? But you see what's going on here. Did you see what just happened there? When I went off the circle and came back here, what was happening, one more time here, what was happening on the circle was simply that this number, this point, was just being translated by alpha. So, I mean, it's as if that red point doesn't even exist. What we're doing in generating, or the fractional part of log alpha, is just rotating around this circle, this unit circle, by length alpha. Okay? So here again is a picture. That's what happens when the fractional part, when the log becomes bigger than 1. Whoop, you see? But okay, so in some sense that red point doesn't even sort of exist as far as what's going on here. So this is how you evaluate the fractional part of n times alpha. You just rotate n times by alpha. So this is not a unit circle in the sense that it has radius 1. It's a unit circle in the sense that it has circumference 1. So when I say I rotate by alpha, it's actually through angle 2 pi alpha. Okay, well, here's a theorem. So Vitali, in his introduction, mentioned some early pioneers in the study of dynamical systems, Boltzmann, Maxwell, Poincaré. These were primarily 19th century, very early 20th century mathematicians, physicists. Another early, late 19th century, early 20th century physicist was Hermann Weyl. And he studied problems that were of a dynamical nature, but had a slightly different, maybe a slightly different focus. So he was interested in taking sequences of numbers on the circle and seeing how they fill out the circle. And he was interested in the property of a sequence of points in the circle kind of filling the circle out evenly, which is what we're hoping is going on with these powers of 2 business, right? Okay, so here's Weyl's theorem. So he says take any irrational number and take any point on this circle, take any interval on this circle, and now rotate p around the circle repeatedly by alpha. Do it n times. Count the number of times that p visits that interval in the first n times. Divide by n. And Weyl says that will converge as n goes to infinity to the length of the interval I. Okay, so that is called equidistribution. Okay, quiz to make sure you're paying attention. What if alpha is a rational number? Is this theorem true? What? No. No? Why? So if alpha instead were rational, notice it's like a dichotomy, right? If alpha is rational, suppose that alpha is, unfortunately I used p here, so suppose as a reduced fraction alpha is r over s. or R and S are relatively prime integers, well, if I multiply by S, right, that number by S, I get R, which is an integer. So if I take the fractional part, I get 0. So if I add P plus R over S, and I do that, add R over S times, I get back to P. So every single, if it's rational, every single orbit is finite. Okay, it's a very different behavior. In particular, you can easily cook up an orbit that does not visit this interval at all. Okay, so clearly it's not equidistributed, this equidistribution. And in fact, equidistribution implies a weaker property that, in particular, every point, if I perform this procedure, it will densely fill up the circle. So the closure will be the whole circle of that infinite set of points. So in particular, it has to visit every interval. Okay. Okay, so now let's use Weyl's equidistribution theorem to answer our original question about powers of 2. Okay, so here's our circle. Here's alpha, which is, by the way, log 2 is irrational. Everyone? Okay, we're all good on that. Does anyone know how to prove that? What? 5 does not divide 2. Something like that, yeah. So it's the classic, the classic proof. Okay. Okay, so here's a picture of the first 10 orbits of that red point. So first 10 iterates of this construction, starting with 0. And as you see, they do seem to be filling up the circle pretty evenly. That's not surprising because it took a full, well, it's not so surprising because these guys are evenly spaced. And at some point, we've come back very close to where we started. So they almost look like they're evenly spread out on the circle. So here's n equals 30. They don't look like they're so evenly spread out. And by the way, the fact that these aren't so evenly spread out is reflected in the arithmetic properties of the log of 2. But we continue, and things start to look more evenly spread out. And now they're looking incredibly evenly spread out. And at some point, it's clearly filling up the circle in some pretty even way. You don't see any hot spots. There's no dark spots or, okay. In fact, it's really evenly filling out the circle. Okay, and so now we just apply the theorem to answer our initial question. We start with 0, and we look at these intervals. Okay, so if at some point the first digit of 2 to the n is 1, then the fractional part of the log of 2 to the n will land in here. And this is first digit, 2, 3, and so on, just to remind you. And so we can put those intervals on the circle, and then we see that the number of times that we visit an interval by Weyl's theorem is proportional to the length of that interval. Okay? And so it's the proportion of points in K is equal to the length. Okay? So that's an application of Weyl's theorem. Okay. Just restating the earlier. Okay. So the fraction of powers of 2 beginning with K is just the length of IK, and we can compute that, right? It's just the log of K plus 1 minus the log of K. It's an interval. So you could write it that way. And that solves our problem. And let's see that. Yeah. So this is the graph of x plus 1 over x. And here is the distribution of primes. Okay, so it intersects precisely, or it should, I guess, anyway. I don't know why it doesn't quite intersect right, but anyway, this is the limiting distribution, and we have computed it using Weyl's theorem. All right. That's kind of cool. So let's go back to Weyl's theorem. I want to restate this in dynamical terms. So I want to start talking a little bit about dynamical systems. So I've been very careful at this point, up to this point, not to use any dynamical terminology, but it's time for me to start doing that. Okay, so we're going to talk about the circle. We've been talking about the circle. The circle is just, we want to think of it as real numbers mod 1. Okay? So two numbers are identified if they differ by an integer. Or equivalently, we can think of the interval mod 1. So the interval where the endpoints are glued. And now if we talk about adding two numbers of the circle, we add them mod 1. So this plus this, we add them. Maybe it's a real number bigger than 1, but then we take mod 1. Okay, so another way of saying this is the circle is an additive group. Okay, so now let's restate Weyl's theorem for irrational alpha. What does it say? It says if I take any point in the circle, I was calling it P before, now I'll call it X, and I take any interval, then, and this is, so I add J times alpha to X, and I let J range between 0 and m minus 1. I take the proportion of times that this is in this interval, then this limit exists and equals the length of the interval. Okay. This can be restated in terms of a dynamical system. I for some reason, didn't make the restatement, even though I kind of wrote down all the terminology that you'd need to make the restatement. Okay, but let me explain what's going on here. So there's a hidden player in everything that we're talking about. That's a dynamical system. What is a dynamical system? Well, going back to the kind of classical vocabulary of the early physicists like Poincaré, we have a set, and we call that set a phase space. So we want to think of that set as representing maybe, say, configurations of a solar system, right? Possible configurations in terms of position and momentum. That's why it's called a phase space. But basically, X can be any set, and depending on what flavor of dynamicist you are, X could just be a measure space, or it could be a topological space, a compact metric space. In the kind of dynamics I do, it's a manifold, a compact manifold. In any case, it's a set, and F is a map from the set to itself. That's a dynamical system. It's about the most basic thing you can think of in the world, okay? So F is a transformation, and X is what we call the phase space. And what do we study in dynamics? Well, the most basic object of study is what we call an orbit. And we've been talking about orbits this whole time. And I've been biting my tongue not to say the word orbit, okay? So I take a point X and X, and here's what I do. So I look at X. I didn't write down X. I probably should have. Then I apply F to X, okay? So I get a point in X again, because X, the domain and the range are the same. And now I apply F to that point. And here's the notation we use, which is very nice. We call it F squared of X. So it just means the composition of F twice applied to X. F cubed of X, F to the fourth of X, and so on. That point, as it moves around, we think of iteration, that is, composition of F with itself, as representing some unit of time moving forward. And the structure of these orbits is a fundamental question in the study of a dynamical system. Okay? And so an example of a dynamical system that we've secretly been looking at all along is the example where X, the phase space, is a circle, probably the simplest manifold that there is. I mean, it is the simplest manifold there is. And our transformation F in this case is just this rotation by alpha. Okay? And what we've been looking at is orbits, the orbit of the point 0 under translation by log base 10 of 2. All right? So that's what we've been doing. And so if we reformulate or redescribe Weyl's equidistribution theorem in this language, it says that if alpha is irrational, then every orbit F of F alpha is equidistributed. And equidistributed just means that it's uniformly distributed with respect to length on the circle. So secretly, there's a measure here, but I don't assume you guys all know measure theory. But secretly, we have a measure here, Lebesgue measure, and it's preserved by this rotation. And now we're saying something stronger. We're saying that every orbit actually kind of gives, you can recapture this measure by just looking at an orbit of any point. Just pick a point, look at its orbit, you recapture Lebesgue. And if you like, it's a way of measuring lengths of intervals if you didn't have a ruler, right? But you could count. Does everyone see that? So if you were interested in doing that, here's a way. Okay. It's not a very effective way. There are more effective ways of doing that, but okay. So that's what Weyl's theorem says. All right. So I'm not going to prove for you Weyl's theorem, but in fact, if you know a little bit about trigonometric polynomials, it's really not, and a little bit of measure theory, it's an exercise. It's an exercise I give to my first year grad students when I teach measure theory, okay? It's not a hard fact. Okay. All right, so now I want to say, okay, so I just told you that if I want to measure the length of an interval, I take my number log 10, and I, log base 10 of 2, or any irrational number, and I take any point and I look at how many times that point visits the interval, and that'll be the length. Okay, that seems in some sense very random, and there is a sense in which this is saying that every orbit is kind of random. You know, it doesn't favor one part of the circle or another. There are a lot of dynamical systems that will favor different parts of the phase space. You know, they go over there and they spend a lot of time there. Now this is kind of random in the sense that it doesn't prefer any location. But is there any other sense in which this orbit is random? And I claim no. Basically, this is as far from random as you can get while still being equidistributed. Okay, so there are quite a few ways of seeing this. And I gave some exercises. I have some exercises in the end for you to do. Maybe that'll convince you of this. But here's a picture that should rather convince you. So on the top is just recalling for you what the orbit of the point 0 under rotation by log 2 looks like after a certain number of iterates. Yeah? The bottom is what happens if I randomly choose a collection of points in the circle. A random collection of points in space does not look like a perfect grid, right? It has clumps, right? I mean, that's why we see cancer clusters, because that's the way random events distribute themselves. They don't sort of fill things up very evenly, they clump, okay? So this is what a random collection of points looks like. You see, even when you've chosen quite a few points, you've got clumps, okay? Nonetheless, if I continue to randomly choose points, it will have this equidistribution. I mean, if I want to compute the length of an interval, I can randomly choose points and count the number of times it visits the interval. But this is what a random thing looks like. That's not. So if someone does a computer, if someone the science of trying to distinguish random from non-random numbers is a pretty sophisticated statistical subject. I mean, in particular, if you want to find out if someone is cheating, right? Or someone is cheating on their taxes, or in a scientific experiment. For example, Mendel cheated. He forged his numbers. And we can tell that because we can see if you look at the numbers that he chose for some of his experiments, they're not random. They don't behave like random numbers. So if I gave you this sequence of points, you would recognize that it wasn't random. Okay? So we have a dynamical system that in some sense is able to fill out a space pretty evenly. Do we have a dynamical system that behaves randomly? So I claim, well, these are the kind of dynamical systems that I'm quite fond of. Okay, I try to understand systems that are actually quite what we're going to call chaotic. Okay, so that's what I just said. The orbits of F alpha are far from random because they're rotations. But what about other dynamical systems? So here's a few just a few dynamical systems on the circle, and I'm going to talk about the second one here. These are kind of the baby examples of dynamical systems on the circle that illustrate quite well, I think, two competing phenomena in dynamics. And this is a much more interesting, I mean, in some sense, this is a way more interesting type of dynamical system. Here we have a parameter A. This is called, so it depends, you have to fix A, just like you fixed alpha up there. This is called the unimodal family of maps. And in fact, the recent, the Fields Medal that was won last week at the ICM by Artur Avila, a large part of it was rewarded on the basis of his work studying this map. So this is a fascinating map. I'm going to just talk about this much simpler one, which is what? Well, I multiply, it's not so far, I mean, it's an elementary operation. Here I add alpha. Here I just multiply by 2, but then I go mod 1. So if I was going to draw a graph, so here's, by the way, what the graph of x plus alpha mod 1 looks like. This is the interval 0, 1. This is alpha here, and this is what happens when x plus alpha becomes 1. It goes back down here. Okay. So, and this is what the graph of 2x mod 1 looks like. It's, you know, to produce the graph, it's just like doing the fractional part of log. First I take 2x, and then I chop off the integral part, bump it down, and I get something like this. Okay, so I just want to describe to you this map. I'm not sure how much I'm going to be able to say about it, but we could put it on the circle and draw a picture. Because some people would like to think about this doubling map. Okay, so I didn't leave any pause. Okay, back. Okay, I'm sunk. Okay, so there you go. Let me see if I can go back and do that one more time. Nope, okay. So what did I just do? I think I can describe to you what I just did. I took the circle, I cut it open, I doubled it to twice its length, and I glued it back. I wrapped it around the circle twice. Okay. So it's called the doubling map. Think of taking a rubber band, stretching it to twice its length, and just doubling it back onto itself. Okay, this dynamical system has very different properties from the rotation that we've looked at before. So let's just go through a few of them. Okay, so let's see. Maybe we can, just a brief exercise, if we have time, see why the first fact is true. So not all orbits are equidistributed. In fact, many orbits are finite. Can someone give me an example of a finite orbit? 0! Excellent. Another one. 1/2, right? Right, because it goes, after multiplication by 2, it goes to 1, which is 0, and then it's stuck there. In fact, I claim that there's a dense subset of points on the circle with finite orbit. How would you prove that? So it's not just like, oh, there's a few of them. They're everywhere. Countable, yeah. N over powers of 2. Yep. I mean, those are all examples of numbers with finite orbit, right? So I just take all the numbers whose denominator is some power of 2. Can you characterize the set of points with finite orbit? Rational numbers. So think about it. It's an exercise. All the rational numbers have finite orbit. And which of them, some of them will come back to themselves after finitely many iterates. Some of them will go and kind of land on a different orbit that comes back to itself. Okay, so clearly it's very different from the rational case, the rotation case. But this almost seems paradoxical. So almost every orbit is equidistributed. So what does that mean? All right, so you kind of have to have the language of measure theory to state this, but let me attempt it. So the rational numbers, they're a large sense in the set in the sense that they're infinite, but they're small in the sense that they're countable. And in particular, if I were to choose a point at random from 0, 1, according to the uniform distribution, it would not be rational. Okay, so you have to believe that there's some sense of measure of subsets of the interval, And it generalizes the notion of length. So the measure of an interval is its length, but you can define measures of more general sets. And the measure behaves in a way that's reasonable. So if I have a countable set, you see I can cover a countable set with a collection of intervals whose total length is arbitrarily small. Right? So a countable set has measure 0. Okay, well, there are uncountable sets that have measure 0 as well. Cantor sets, middle thirds Cantor set has measure 0. Okay, so in some sense, let's regard those sets as being not likely to occur in nature. Okay, I mean, this is the kind of thing that Poincaré was interested, or Boltzmann was interested in understanding, is what kind of would happen if you kind of picked a configuration at random and then let it evolve according to a set of rules. So what I'm saying here is if I pick a single point at random, so there's where the randomness takes place. I have to pick a point at random. But then I let the dynamics do the work, meaning I just apply this set of rules, multiplication by 2 mod 1, and I will get an equidistributed set. Okay, well that seems, first that seems worse than rotation. Right? Every orbit is equidistributed with a rotation. Here, I have to pick a point at random and then look at its orbit. But something much stronger is true. So, in fact, if I take almost any point and I look at its orbit, it will be indistinguishable in any sense you want to look at from a random sequence. Okay? So just to remind you, this is what an orbit of a rotation looks like for an irrational alpha. And here, okay, I'm not telling you how I generated the sequence. Actually, I went on to Google Images and stole something from the mathematical website. But I could lie to you and say, look at this. I've chosen a point at random, and then I multiplied by 2 mod 1. I looked at its orbit under the dynamics, and this is how it would look. Okay? It's indistinguishable in some very strong sense. Okay? So. Okay, so the rest of this talk is basically words. I know the mathematical content has not been large, but I want to really get some of these ideas across. So the doubling map is what we would call a chaotic. It's the simplest example of a chaotic dynamical system. And by chaotic, I just mean the orbits behave in a very unpredictable way. They're predictably unpredictable. They behave like a random process if you look at them right. Okay? So we have this kind of dichotomy between chaotic systems and regular systems. And I think the language that Vitaly used was stochastic versus deterministic. Okay, same dichotomy. So there's a place in dynamics, in life, for both kinds of features. But we really want to think of these as opposite features. This kind of dichotomy, it occurs everywhere. And to understand what can happen in the most chaotic sense and in the most regular sense is how you understand dynamical systems. So for example, the proof by Ben Green and Terry Tao that the primes contain arbitrarily long arithmetic progressions. Well, it really comes down to looking at a dynamical system and understanding both kind of chaotic possibilities and very regular possibilities. So, so that's kind of the kind of yoga, the mantra that we carry in our heads in dynamics is to try to understand these two extremes. So one kind of very interesting feature of chaotic systems is that they tend to be robust. That is, if you start with a chaotic dynamical system and you kind of make some errors in your computation of it, or you add a little perturbation term, it stays chaotic. Whereas these rotation systems are very rigid. And so if you have a rotation system, you can often, a rotation-like system, you can often nail it down what it really is. You can say, that's actually just a rotation on a circle, or it's a rotation on a compact group, or something very similar. You can tell by looking at the orbits that it's a very special system. The dynamics lead the way. Okay, so I said I was going to end with an open question in dynamics. So what do I study? I study dynamical systems where X, the phase space, is a manifold, a smooth manifold. So that's the kind of dynamics that's kind of the setting that was originally, it's kind of relevant to the kind of questions that Boltzmann and Poincaré and Birkhoff were thinking about. And F is a diffeomorphism. It's smooth. You can differentiate it, and it has a differentiable inverse. And that's 50 minutes, so okay. Okay, so here's an open question. Take a surface. Can you find the following type? Can you find a smooth map of the surface, infinitely differentiable with an inverse, where you have a coexistence of two phenomena in the same map, regularity and stochasticity, or chaos? Conjecturally, yes, and it seems obvious if you look at examples that this occurs. No one knows how to prove a single example of this on a surface, okay? Yes? Do I have an example? Well, I can give a conjectural example. Right, there you go. So I haven't written down a formula, but I can write down a formula. In fact, it's very simple. Basically, you take the map. No, I'll write it down. If you're interested, I can show you the formulas. But here's an example that I took off of some physicist's webpage of what one imagines is a map where we've drawn some orbits here. It's not just one orbit, it's a bunch of orbits. It seems pretty clear that here, this is very chaotic, right? It just looks totally random. Here, clearly, these circles are what you would call regular, right? Okay, so in fact, the existence of these circles has been established. A large set, like a positive measure set of these circles, has been established by the work, it's something called KM theory, so by the work of Kolmogorov, Arnold, and Moser. I mean, this is one of the fundamental achievements of the mid-20th century, was the work of Kolmogorov. But the existence of this as being chaotic, no one knows. And so you say, well, so what? Well, I mean, it's not just that coexistence. I mean, it's an interesting open question, but really this seems to be just a fundamental mechanism that occurs in real life. Here's a picture that comes from the study of particle accelerators. Here's the North Pole of Saturn. Right, this isn't exactly a deterministic, I mean, it's not exactly a dynamical system in the sense that I described it, but it's well approximated by one. This is life as an algebraic geometer would consider life, a particularly ardent one, right? So this is kind of this coexistence phenomenon occurring on what's called a K3 surface. I mean, this isn't a K3 surface, but it's part of it. It's a slice. Okay, so I just wanted to end on some exercises, which I'll leave up. So to really check that you understood everything, I would like you, whoops, where did X go? Shove it any real number. So suppose I take the number 5, or I don't know, pi. Let's take pi, and I multiply by 2 repeatedly. And I look at the first digits. Show that the distribution of the first digits is the same as the distribution of 2 to the n. Yeah? X is not 0. What? Yeah, I mean, okay, good. So someone's giving me an answer right off the bat. Another way of phrasing this is, this amounts to looking at the orbit of log x under rotation by log 3. Okay, and so that's going to be equidistributed. Every orbit is equidistributed. Okay, so it's the same. Here's an interesting one. I can uniquely determine a number between 0 and 1, or let's say a number between 1 and 10. You have to fix some reasonable interval. If I look at the sequence of first digits, it completely determines the number. So it's all encapsulated in that information is encapsulated in, the number itself is encapsulated in that sequence of first digits. So this is an example of using a dynamical system to generate a name of a number. Here's my name for the number x. I multiply it by 2 to the n. I take the first digit, I get a string of digits. That's my name for x, and prove that that name determines x. Okay, this is a good one. if you have it in a measure theory, try to prove a baby Weyl theorem. So prove if you have an irrational number, then the orbit of every point under that irrational rotation is dense. So it's not equidistributed necessarily in every interval, but I'm just asking you to prove it visits every interval. It's a pigeonhole principle proof. It's a good one. Okay? And finally, we haven't talked much about this dynamical system, but this dynamical system generates a very natural naming of numbers between 0 and 1, this doubling map. So taking a point and looking at its orbit, we can write down a name for that. And that name, if you figure out how you write down the name, it's not too hard, will actually correspond to the base 2 expansion of the number x. So that's just the beginning. You can think more about this. There's a way using a dynamical system to generate the continued fractions expansion of a number and other names for numbers. But I think it's time for me to stop.